of signal Cn. For part A, I have used MATLAB code to plot the signal Cn. The waveform clearly show how the signal behaves over time. This helps us to basically analyze the properties of the signal. B. Length of signal S1n. For part B, the signal S1n is defined from n0 to n60. Therefore, the length of the signal is 61 sample. I have calculated and confirmed this. For part C, to determine whether S1n, I analyze the values of the signals. The smallest value of n that satisfy Sn equal to Sn plus n is called the fundamental. For part D, E, and F, I have done with MATLAB. For D and for E, I have determined whether S2 by using mathematical manually, and after part of number 1, I have found out the dissimilar between S1n and S2n.
Hello, my name is Aina. I am representing my group to present our solution for question 2. In this question, we were required to generate a continuous time-damped complete sinusoid signal using MATLAB. Based on the equation xt equal to 5 exponent negative 0.3 t exponent j6t for the time range t equals 0 to 6. Our first step was to write MATLAB code that plot the real and imaginary part of the signal in one figure, and the magnitude and task in another. We use functions like real, image, ABS, and angle to display all four components clearly. This plot helps us visualize how the signal decay exponential while oscillating, which is typical in signal processing and control systems.
Hi everyone, in this presentation, I walk you through question 3 on discrete time signals and systems, focusing on signal generation, plotting, and convolution method. For part A, we're given 3 discrete time signals, H1, H1n, H2n, and Xn. These are defined using delta and step functions, and we need to evaluate them over the range, negative 6 and to 6. Let's take a look at how we implement and plot them in MATLAB. Here's the breakdown. H1n is a combination of shifted delta functions. H2n uses the unit step and a scaling factor. Xn is a ramp signal multiplied by a rectangular window from n equal to 0 to n equal to 4. Using MATLAB stem and subplot function, we visualize all 3 signals in a single figure with proper labeling. As you can see, we get clean plots of all 3 signals over the specified range. For part B, next we assume a system hash composed of 2 subsystems, H1 and H2 in cascade. Here's how the signals flow through the system. Input Xn goes into H1, output of H1 Vn equal to Xn times H1n, output of H2 Yn equal to Vn times H2n. We use the MATLAB 0 and V function to perform both convolutions. Note that after each convolution, we compute the appropriate time axis to correctly plot the result. Here are the result of the convolution. The first plot shows Vn and the second shows Yn, the final system output.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nazim and I'm gonna talk about question 4. For question 4, I've calculated the convolution of xt equals to try t minus 2 over 3 and ht equals to power of negative t sine t u t. I've used MATLAB to perform a numerical convolution and plot xt, ht, and yt. Then, I derived the analytical integral. Finally, I saw that the shape and duration of both signals influence the output's time, range, and shape.
Okay, Assalamualaikum and good evening. My name is Raif Danish bin Bani. Metric number S73026. We'll be explaining question number 5, impulse response and square wave input. Okay, in this question, we work with a sine-based filter. Firstly, I plot the impulse response Ht. Then I convolve it with 2 different inputs. For 5b, I use a sine function sine for t, while c, I use NA square we've built using 20 Fourier harmonics. In both cases, the output Yt was smooth because the filter suppresses high frequency noise. Okay.
Hi, my name is Nazim and I'm gonna talk about question 6. In question 6, I analyzed a system using Laplace transform. I used MATLAB's residue to find the impulse response, which is Ht equals to 1.6667 e with the power of negative 4t plus 0.6667 e with the power of 2t plus 0.6667 e with the power of negative t, and t is bigger than 0. Then, I found the transfer function from the different equation, convert it to zero-pole gain form, plot the pole-zero map, and verify that the system is stable using its table. This helps understand system behavior in the frequency domain.